Now let's look at a rubber block sliding across metal. That is the gray top line right here. And below it we have a rubber block sliding across ice. Well, as expected, the one on ice is going to slide a lot farther. And why is that? Because there's less friction. So is it okay to say that friction resists motion? Because that's clearly the case here. In just a minute, we're going to see why that's not great. There is more friction between rubber and metal than between rubber and ice, and this means the top of the rubber block changes its motion more rapidly than the bottom block. The bottom block has this slowing down that's happening. Meanwhile, the top of the block is sliding across faster. Here we go. So we were just dealing with rubber blocks. Now we're looking at a box with rubber tires. More friction on metal, less friction on ice. The car on the metal speeds up more rapidly and the car on the ice speeds up less rapidly. This must mean that friction helps both cars speed up, and more friction means better speeding up. When friction opposes motion, we call it friction. When friction helps motion, we call it traction. So if you find yourself driving on ice, it's dangerous. There's less traction. You don't have as much control of the car as you think you do. When you are trying to speed up, as you see here, it takes a little bit to get going. You see some of the slipping going on. Well, the same can be true if you're accelerating in the opposite direction, trying to slow down. You're not going to slow down as smoothly as you do when you do have a lot of friction or a lot of traction. Friction and traction are the same force, mean the same thing. Onto elastic springs, or elastic force. If an object is connected to a string or a rubber band, the spring is stretched, then the spring exerts a force called the spring force, or the elastic force if you prefer. The direction of the spring force is always opposite the direction of the spring attached. The spring is stretched to the right. The spring exerts its force to the left, as the spring exerts force to return to its natural length. If the spring is stretched to the left, the spring exerts force to the right to get back to its natural length, right? So you pull a spring, it's going to bounce back. Springs obey Hooke's law, which says the force exerted by a string is directly proportional to the spring's stretch length. That's a typo right there. A force exerted by a spring is directly proportional to the spring's stretch length. The equation, not every force has its own equation. Some of them do. Here's an example of one that does. The spring force equals kx. Fs is the force the spring exerts. K is the spring's force constant. Sometimes it's called the spring constant. It's a number that's greater when the spring is stiffer or hard to stretch out. So you can think of K as kind of the springiness. The lower the number, the more bouncy it's going to be, or the easier it's going to be to deform it, to pull it apart or let it retract. The springiness of the spring. X is the spring's stretch, the difference between the spring's length right now and the spring's natural length. Rubber bands don't obey Hooke's law because the equation that relates the force and the stretch of the rubber band is more complicated. It is not directly proportional. On your equation sheet, your equation will look like this, where it's absolute value signs. Though that absolute value is just a reminder that we're only looking at the magnitude of the spring's displacement from its equilibrium. Equilibrium is the point where the spring is at rest. As soon as you start pulling it, now it is some distance away from X. Spring! It's at equilibrium. It's at rest. As soon as I start to pull it, this extra distance that I pull it right here that is the X. It's not the full length of the spring, it's just how far did I actually move the spring. I don't know if you can see me, so I'm going to do it one more time. Stretch. Equilibrium. My displacement is just this little extra piece right here that I'm pulling it. Okay. It doesn't communicate the direction of F or X, which is why it uses the absolute value bars. With a spring, if I pull on the spring, the force is going to want it to go back towards equilibrium. And if equilibrium was here, when I compress it, the force will want to bring it back to equilibrium, because that's where springs are happiest, at equilibrium. Drag force. Air resistance exerts, if air resistance exerts a notable force on an object, then we have to consider drag, which is the force that air exerts. Drag is like friction, and the drag force tries to prevent objects from moving through the air. However, what causes drag is different from what causes friction. Like this. So if you imagine that to be one surface, and then that to be another surface, those teeth are going to come in contact with each other. And as you rub, it's harder to come, let's say we're going in this direction to the left, it's harder to overcome this mountain here. So you have to push a little bit harder to get it to move up. So it's useful to think of friction like that for a lot of people. Done with draw. 99% of the time we ignore air resistance. We pretend that air resistance doesn't exist, or it's so small we can ignore it. That's not 100% of the time. Never consider air resistance unless you are specifically told that air resistance matters in a problem. There will be cases, especially if you're dealing with calculus-based physics, where you are given an equation and you have to determine the drag coefficient, or you just have to include air resistance, or you need to find terminal velocity. But for the most part, we can ignore air resistance because it is so small and it's not going to affect any real outcomes. If I drop this little thing, pretty small surface area, really close to the Earth, it's not falling a great distance, air resistance isn't going to do a thing to it. Air resistance will do something to this poor student's quiz. As I drop it, you can see the paper stays up. If I put it behind something, that will just plow right through that air resistance. Then the paper falls right down. Try it. Applied force, specifically the force of the hand, and we're going to talk about that in the next video.